Welcome to this next video in the short series describing acid-base chemistry. In previous videos, linked in the description below, we saw definitions of acids and bases developed through time. Specifically, strong acids and bases were described as species that dissolved completely in water, with the six strong acids being HCl, HBr, HI, HNO3, HClO4, and H2SO4. Similarly, there are only 7 strong bases that dissolve in water. The 5 group 1 hydroxides, lithium, sodium, potassium, and rubidium hydroxide from group 1, and cesium, and from group 2, strontium and barium hydroxide. Outside of those 6 strong acids and 7 strong bases, all other acids and bases are weak, meaning they dissolve completely in water. A weak acid is any given species where HA is in equilibrium with H plus and A minus, and as an equilibrium reaction, it has an equilibrium constant, product over reactants, called the acid dissociation constant, which is conveniently given a subscript A for acid. Similarly, any weak base, B minus, when placed in water, will attract the proton to give you OH minus and HB, and again described by an equilibrium constant, in this case the base dissociation constant, products over reactants, with the water as the solvent not included, symbolized conveniently with a lowercase b. We also learned about the following about acid-base reactions. First of all, they all have to occur in water, and water has a unique property known as being amphoteric, meaning it can either act as an acid or a base. When one has weak acids and bases in water, they actually exist in pairs. As you can see from the description, from the balanced equations above, HA goes to the base A minus, B minus turns into the acid HB, conjugate acid-base pairs. Additionally, it was discovered that water itself is chemically active. It exists in equilibrium with an equilibrium constant, Kw, equal concentration of H plus times OH minus, always equal to 1 times 10 to the minus 14th. This comes in especially handy because for any conjugate acid-base pair, Ka times Kb is equal to the water dissociation constant, meaning that you only have to know either Ka or Kb, and you automatically have the conjugate figured out. Finally, we learned an easy way of determining whether a solution is acidic or basic. That is the concept of pH, the negative base 10 log of the proton concentration, where a neutral solution has a pH of 7, an acid solution would have a pH of less than 7, and a basic solution has a pH of greater than 7. In this video, we will look at acid-base reactions, of which there are essentially 4, since either acids or bases can either be strong or weak. The first reaction would be the addition of a strong acid and a strong base. A strong acid such as HCl and sodium hydroxide as the base will donate the following protons into solution. I will get an H plus and a Cl minus from the HCl, an Na plus and an OH minus from the sodium hydroxide. Rearranging those protons, H plus and OH minus gives us water, but sodium chloride is still soluble, so I would still get an Na plus and a Cl minus. As these appear on both sides of the balanced equation, they're going to cancel out. Therefore, the only thing I'm left with for a strong acid and a strong base is H plus OH minus gives water, meaning I have what's called the neutralization reaction, and at the end of the reaction, the pH will be 7. If, on the other hand, I react a weak acid such as HA, with a strong base, anything that donates OH minus, you'll see the H plus will be donated to the OH minus to give water, and the remaining A minus is now the conjugate base. So any weak acid plus strong base produces the conjugate weak base, and therefore the end point of the reaction will have a pH of greater than 7. If one flips that around and reacts a strong acid donating H plus with any weak base, B minus, it's simpler to see that H plus and B minus will be attracted to give you HB. This HB would be the conjugate weak acid of B minus and give a pH of less than 7 at the equivalence point. So we've had strong with strong, weak with strong, strong with weak. The final possibility, a weak acid plus a weak base, gives something completely new. A weak acid plus a weak base gives something that's called a buffer, which will be the subject of the next video in this series. One thing to notice in these reactions is that weak never gets converted to strong. A weak acid is reacted to give the conjugate weak base. A weak base reacts with a strong acid to give the conjugate weak acid. These acid-base reactions are investigated using a technique known as a titration. A titration is a quantitative technique where one takes an unknown, in this case, some volume of acid with an unknown concentration, and compares that to a known. The known is added through an apparatus called a burette, essentially a graduated cylinder with a valve on the end that allows a known rate of delivery. That is filled with a base with a known concentration. One other thing is needed to do the titration, and that would be an indicator. An indicator is simply a weak acid that changes color. Between the weak acid and its conjugate weak base, the acid has one color, the base has a second color. So, one starts the titration by adding a measured amount of the base, of the known base, to the unknown acid. The equivalence point stops when the colors change. The equivalence point is the point where the end of the titration, where the moles of acid and the moles of base are equal. To understand an acid-base chemistry will require going into titration curves in some detail. We'll start with the titration of a strong acid and a strong base. Specifically, 35 milliliters of 0.1 molar HCl will be titrated with 0.085 molar sodium hydroxide, a strong base. Several things will be determined. First of all, we would need to know what would be the initial pH of the HCl solution. HCl is by definition a strong acid, which means it will dissolve in water to give H plus Cl minus. Therefore, if I have 0.1 mole per liter of HCl, and HCl gives 1 H plus, I have a 0.1 molar H plus solution, and the definition of the pH is the negative log of H plus, or the negative log of 0.1. So I would have a solution initially with a pH of 1. Second thing that's needed. What volume of sodium hydroxide is needed to get the equivalence point? The equivalence point is when moles of acid and base are equal. My 0.1 mole per liter in 0.035 liters, or 35 milliliters, gives me 0.0035 moles of HCl, or 0.0035 moles of H plus, since I have a strong acid. One acid reacts with one base, which would mean I would need 0.0035 moles of hydroxide. On a 1-to-1 relationship with sodium hydroxide, I need 0.0035 moles of sodium hydroxide. And at 0.085 moles per liter, I would need 0.41 liters or 41 milliliters. Third thing to know, what is the pH at the midpoint of the titration? With a strong acid and a strong base, half of that acid will have been neutralized. I will have also added half of my 41 milliliters of base, so the volume will have gone up. So at the midpoint, I have 1/2 of my original 0.0035 moles of H+. I have my original 0.035 liters, plus half of the 41 milliliters that I was going to add. That gives me a 0.032 molar H+ solution. That gives a pH at the midpoint of 1.5. The final thing to know, what is the pH at the equivalence point? Since I have a strong acid and a strong base, my reaction is to make water. I have a neutralization reaction. Therefore, at the equivalence point, the pH is going to be equal to 7. Now, if one constructs a titration curve with this data, a titration curve where pH is on the y-axis and volume of base is on the x-axis, we now have 3 points. At no volume of sodium hydroxide, the initial pH is 1. At the midpoint, approximately 20 milliliters in, the pH is now 1.5. And at the equivalence point, at 41 milliliters, the pH will be 7. Taking all the points in between with a strong acid and a strong base, one winds up with a very symmetric S-shaped curve. Performing the exact same procedure on a weak acid and a strong base gives a different and much more detailed conclusion. If I take 35 milliliters of a 0.1 molar CH3CO2H acetic acid with a Ka of 1.8 times 10 to the minus fifth and titrate that with a 0.085 molar sodium hydroxide strong base solution, we'll look at the exact same procedure as previously. First of all, I know that acetic acid is a weak acid because it's not one of the 6 strong acids, and I'm given an equilibrium constant, which means it exists in equilibrium. So, if I look at the initial pH of the solution, I now have a weak acid, which I know exists in equilibrium, and I define the balanced equation for that as CH3CO2H in equilibrium with the conjugate base, and also define Ka as products over reactants. At this point, as with all equilibria, the next thing to do is set up a table where you have columns that contain the 3 reagents, the CH3CO2H, H+, and these acetate ion. And the rows are always asking the same 3 questions. What was your initial amount? How much did that change? And what is the final amount? In this case, we know the initial amount was 0.1 molar. We also know that if we start on the left, the equilibrium has to shift to the right. So at the end, we have 0.1 minus X, X for H+, and X for the acetate ion. So, Ka is now X times X divided by 0.1 minus X. This is a quadratic, which can be difficult to solve. One can attempt to simplify this by making the assumption that X is going to be a very, very small number. Therefore, 0.1 minus x can be rounded off to 0.1. Doing this, we get an initial concentration of H plus of approximately 1.3 times 10 to the minus third molar. One cannot just make assumptions without checking them. In order to determine if this assumption was correct, one replaces the value obtained into the original equation. As you can see, this gives a slightly different answer of 1.82 as opposed to 1.8. However, that 1.4% error is within 5% acceptable experimental error. Therefore, my assumption is acceptable, and it is acceptable to say that X, the concentration of H plus, is to a large degree of certainty equal to 1.34 times 10 to the minus third molar, which now gives an initial pH of the solution of 2.87. Moving on, the second part of the equation, or the question rather, the volume at the equivalence point. This, it should be noted, is that it's irrelevant whether you're talking strong acids and strong bases or weak acids and weak bases. The equivalence point is simply the point where the moles of acid and base are equal. So once again, I have my 0.1 mole per liter in 0.35 liters. I have 0.0035 moles of acid. That will once again require 0.0035 moles of base to react with it, where my sodium hydroxide gives 1 OH minus. So I would need 0.0085 moles of sodium hydroxide. In a 0.085 molar solution, this would mean I would need 0.041 liters or 41 milliliters. The third part of the question, what is the pH at the midpoint of the solution? This winds up being a very, very important question. With regards to a weak acid and a strong base, if one reacts a weak acid and a strong base, one produces the conjugate weak base. If I look at any weak acid as an equilibrium constant of H plus A minus over HA, at the equivalence point, all of my HA has been turned into A minus. At the midpoint, I am 50-50, so A minus is equal to the concentration of HA. Essentially, at the midpoint of the titration, Ka is equal to the hydrogen ion concentration times 1. The following is always true. At the midpoint of a titration of a weak acid with a strong base, the pH is simply equal to the pKa, or the negative log of the Ka value. In this case, at 1.8 times 10 to the minus fifth, I wind up with a midpoint pKa equal to 4.74. What is the pH at the end of the solution? Again, I have a weak acid plus a strong base giving me a weak base. So, I initially had 0.0035 moles of my weak acid. That would have been turned into an equal moles of weak base. But while doing the titration, I also increased the volume. So at the end of the titration, I have a 0.046 molar solution of weak base. And since I have a weak base, I would need Kb, which is Kw over Ka, of 5.6 times 10 to the minus 10th. So the pH of the solution at the equivalence point is essentially asking, what is the pH of a 0.046 molar acetate ion solution with a Kb of 5.6 times 10 to the minus 10th? Since this is a weak base, it exists in equilibrium, and one handles it like every other equilibrium problem. First, one needs a balanced equation where the weak base will react with water to give the conjugate weak acid plus OH minus. Secondly, I have a value of Kb. I need to define Kb in terms of product over reactants. The hydroxide concentration times the acetic acid over the acetate is going to be numerically equal to 5.6 times 10 to the minus 10th. Again, in equilibrium, one sets up a table with the reagents involved being the columns, and the initial state, the change, and the final state being the rows, where I know I initially will have no product. Therefore, the reaction will have to shift to the right and subtract from the left. So at equilibrium, my Kb is going to be equal to X molar acetic acid, X molar hydroxide, or 0.546 minus X acetate. Again, I can assume that X is going to be very small. So I can assume 0.046 minus X is essentially equal to 0.046. And I can solve for X. Before proceeding, again, you don't walk away from an assumption. One has to check it. By placing that assumption into the initial equation, in this case, performing and producing no error. The other thing to note at this point is in solving for X, one solves for the hydroxide concentration. So one can find the pOH of the solution of 5.3. Also remembering the relationships between acids and bases, pH plus pOH is equal to 14. So at the equivalence point, I have a pH of 8.7. If I look at the titration curve once again for this reaction, where the pH is my Y and the milliliters of base are my x-axis, I have an initial pH of 2.87. At the midpoint of approximately 20 milliliters, the pH goes up to 4.74. And at the end, I indeed have a basic solution. The conjugate weak base gives an equivalence point pH of 8.7. Connecting all the points in this curve gives a radically different view. I now have, instead of a single sharp S-shaped curve, I have a two-step curve. Pairing the two of them gives a good deal of insight. For a strong acid and a strong base, one winds up with what is called a sinusoidal or S-shaped curve that is highly symmetric. In this case, the equivalence point is known to be 7 and is a point of inflection. Meaning, at that point, the curve essentially mirrors itself. It goes from being over and up to being the identical curve of going up then over. If one looks at the titration curve for a weak acid and a strong base, again, reproducing what we saw, one sees a stepped curve. In this case, it's asymmetric. Also, it's very difficult to determine what the equivalence point is. As mentioned, the equivalence point is a point of inflection. That means it is a maxima in the first derivative. So for a weak acid and a strong base, one needs a secondary y-axis where one measures the change in pH with the change in volume. This will be a relatively flat curve until you reach a spike. That spike, or that maxima, is the point of inflection in the curve, and it's also the equivalence point. More importantly, or with more significance, one will notice Near the midpoint, the plot goes flat. The slope goes to 0, and which means I have a constant pH. This is a clue as to what the next video is. This region is called the buffer region. If you recall previously, at the midpoint, the concentration of weak acid and conjugate base are equal. pH is equal to pKa. That creates a buffer that keeps the pH constant. And we will be investigating buffers in the next video in this series. I hope you found this video useful, and thank you.